So I should mention before, actually, also being in Jülich, I was in California, and we just started about a year ago building this new institute in Jülich on neuromorphic software and algorithms. What you'll be hearing today is probably a little bit different from the more neuroscience talks that were here yesterday. Unfortunately, I wasn't here and I couldn't watch them through streaming, I guess because of problems here. I hope it's working now. It is awesome. And so since this topic may be a little bit different from what you're used to, I really like this to be more of a didactic presentation. Feel free to interrupt me and raise your hands. I prefer it that way. And so this way I can also gauge how technical I go in the presentation. So my core interest is about learning. Ever since I finished my PhD, I really wanted to understand how we can build systems that can learn online in the real world. During my PhD, I was building these neuromorphic hardware, similar to what you saw just earlier with two speakers. But we were just programming them to solve some problems and we handcrafted the networks. The question came then, so how can we learn these networks? And so one of the, what that figure is showing is one example I like from the group of Tenenbaum that is showing that if you are presented these three objects, which they call tufas, you've probably never seen them before, but you can very easily spot the other tufas on this grid of images. So you've learned the concept of tufa just by looking at these three examples and very quickly. This is something that conventional artificial neural networks cannot do. You can, of course, extend them so that they can solve this problem. And so that's what we'd like to understand and also build the networks that can solve these problems and thereby maybe gain some understanding in the neuroscience, but also in the engineering of these systems. So I have a couple of preliminary slides on the neuromorphic engineering aspects. So you heard this earlier, so I'll go very quickly to it. So we take the models that are found by computational neuroscience, by you, and we build the circuits, either mixed signal circuits or now using emerging devices to emulate them. So this is different from a normal simulation on your computer in that if I would go in and actually plug a probe onto the chip, I would probably break it, but if I can actually go and read from one of those transistors, you'd actually see the traces that would correspond to some biological-like states, like membrane potentials and so on. And the goal of this research originally was really to understand the brain by building it bottom up. So starting from the transistor, which by the way is used also in a different regime compared to our digital computers, we can build from the bottom up neurons with different synapses and large networks and so on. And once we have this network, we can break it down and analyze what we find. And so going into this virtuous loop of analysis by synthesis. Now the focus, my focus, and also the focus in the neuromorphic computing engineering has also shifted towards using these technologies as an actual practical technology. Why is that useful? Well, here's a very simple stickman example of what these chips are actually doing from the outside, from an architectural point of view. Now, every one of these sticks here is a neuron with its synapses, and this is neuron 1, 2, 3. It is outputting action potential, so all or none events, just like intergradient fire neurons would do. And these events are written on a common bus. So you see here, what you see is actually the address of the neuron that spiked, 1, 2, 3, 4, 5, 2, 3, and so on. So you can, by the way, notice that there's no time written on this bus because time can represent itself whenever that event occurred is when we want it to occur. And so we don't need to give time to it. These are then decoded at the receiving end. So this is at the architectural level, how the communication works. Now, why is this interesting as a technology? So one thing you might immediately see is that the only thing that is communicated from one processor, which is now this neuron, to another processor is just the spike. So it's a very efficient communication protocol. And everything else is local to the neuron. Okay? So this architecture is very scalable. We can build a lot of neurons. We can, in fact, those chips that we can build, we can just have multiple of them and just copy paste essentially the layout for each of those neurons. this is very scalable, but it's also very challenging. How can you do computation and learning with all that local information? Neuron 2 can only sense what Neuron 1 is doing through these all or none events. If you just apply classical machine learning or any computational algorithm and want to apply it to these chips, you'll have problems because they need some information that is not local. Okay, so our goal is really to tackle that question. Like many others, I've been also very seduced by what machine learning and what is called today as artificial neural networks can do. And so we went towards machine learning to understand and build a bridge between what we know about neuroscience, the software simulations, and also the hardware that is used for machine learning. And so you can think of this as kind of a not only top-down, but also not only bottom-up, but also top-down approach, where we take what we know, the theories of machine learning, and we try to kind of fit it to what neuroscience can do. And so we call this a middle-out approach. And you can note that when we build these networks, it also gives us access to all the tools that machine learning has. Right? So GPUs and all the other fancy accelerators, one of them I'll be talking more about today, to actually simulate our spiking neural networks. And this has led to, surprisingly, even today, actually practical applications. So I'll start with the simplest model as a tutorial of how we can build that link to machine learning. This is the intergenic fire neuron model, written slightly differently, maybe from what you're used to. Usually we write them as differential equations, but you can also write them as discrete update equations. So we have here that the membrane potential of a neuron at time t+1 is equal to the membrane potential at time t, scaled by some leak term here, beta, which is usually between 0 and 1, but close to 1. And we have some input spikes that are weighted, and this minus s of t here. So s is the spiking of the neuron itself, which is the step function with the threshold of 1. This is like a reset term. Every time the neuron spikes, it brings it down to 0. So you should know, you probably know this, you've seen many times. So what I'm going to do is just to write this out in terms of nodes, which represents the variables, and arrows which represent how those variables are transformed. So this u of t, so these nodes which represent the membrane potentials. They transform the membrane potential into spikes according to some step function, hence this arrow here. The different columns here represent different time steps, right? Because we have a dynamical system, we're going to have to represent the states of these neurons at different time steps. And so I'm just adding the different transformations for that intergenic fire neuron here. So we have now this leak term, which basically transforms the membrane potential u of t to t+1 by multiplying with beta. Which basically connects this in time. Same with the weights. So we have basically that the input spikes are integrated into the membrane potential, basically just added to them like this. Now we can also have recurrent connections. I didn't talk about that, but you can have the spikes of the network feedback to itself and so on. So why did I present it like this? Is because if you just look at this graph, this computational graph, it's actually exactly the same graph as what people used in artificial recurrent neural networks. And this was a very simple observation at the time, but the fact is that if you can represent it as a recurrent neural network, then we can use all the tools that the machine learning people have developed since the 80s in order to actually train these networks. And so that has led to this kind of gradient-based approach for learning in spiking neural networks. You can use basically the same overall approach of defining some objective function that defines how good you are at some task you're interested in. You can have this be, for example, recognition for classification, but also things like navigation, detection, control algorithms, as we saw earlier, but also planning of trajectories. So all of this can be built in terms of some objective function, which is a scalar. And this objective function is, of course, a function of the network outputs itself. And so, by the way, the story that I'm telling you is the same as in a conventional neural network. You just have some COMNETs or MLPs, an output of which is fed into some classification loss. That's exactly the same story, except that now that we know that these the spiking neurons are artificial recurrent neural networks, we can use those networks in the loss function. And so this is the same story as we had before. There's an additional line here. I'll explain that in a second. But this is basically the interunified neuron. Once we have this neural model, so what we can do is just apply the rules of gradient descent. So we can change the weights or any parameter that you like in this network to decrease this loss function and basically train it. What this means is that you can apply gradient backpropagation to this network. There's one challenge here, and which was going to explain this particular line here, which is that we cannot directly compute all the terms in this equation. See, there's one problem here, that this theta prime, which is, by the way, is written here as the derivative of the activation function with respect to the membrane potential. That is, there's basically the activation function being a step, it doesn't have a derivative. So a very simple trick to solve this problem was just to replace that function with either the rate activation or just some function that is convenient for you, but only when you're calculating the gradients. So this approach is called the Surrogate Gradients approach because it's as if you're defining two networks. One, that's your network that would be operating when you're trying to solve your problem, and the other one that you're using just to calculate updates, gradients. This one can be, we can actually differentiate it, and so but this one we cannot. So the trick here, and it's an approximation, is to take the updates from this one and apply it to this one. And it turns out that this works surprisingly well, not for hundreds of layers as people do in deep learning, but you can do it for 5, 10 layers pretty well. And so, and the idea here is really that, just to get some intuition, these spikes basically define a loss landscape that's step-like. And so a step doesn't have a gradient, so this ball can't go down this valley here. But what we do with the surrogate gradients is that we define this network that's hopefully on top of the, whose loss function is on top of the other one. And this allows the ball to roll down the landscape in a similar way that we would hope here. This approach, therefore, makes these spiking neural networks compatible with gradient backpropagation. Just recently, actually a couple of months ago, I was on the defense of one student, Loïc Cordon, who was in the University of Nice in France. I was really impressed at how far they took this idea of surrogate gradients to solve actual practical problems. So they, in fact, the student was working in collaboration with Renault, so they're interested in doing automotive driving. And so they looked at detection tasks, detecting cars and pedestrians and so on. And they built, I'm not giving the details here, but a fairly large network with millions of parameters, all trained end-to-end using the surrogate gradients approach, and let's see if this works. And this is the kind of result that they get. So if you, by the way, you might notice that these videos are weird. They're not images. It's because they're using a spiking vision sensor called the dynamic vision sensor, or in this case, it was one from the company called Prophecy, which only detects changes. The nice thing about these sensors is that they just provide spikes, events. So if there's nothing happening, basically blue here or dark blue means no event occurred. And as you get more events at a pixel, you get these yellow events. And you'll see that it detects, not always, so you see it didn't really detect this, well, actually it does detect this pedestrian, but it doesn't detect all the pedestrians. It doesn't work perfectly. But given that this is a full spiking neural network, this kind of thing was unimaginable, say even 5-10 years ago. We didn't even know how to train these spiking neural networks 5 years ago. Just for information, so the measure that they use for success isn't accuracy here, but it's something called this MAP, so mean area precision. I think I'm not sure about the terms, but so you see that they're quite far from the state of the art. These are artificial neural networks. These are spiking neural networks. But you can also see that their network is also fairly smaller, and it also has sparse activity. And they also show that this can lead, because the network is sparse, it doesn't have to compute that much. It can actually be more energy efficient than a conventional processor. So it's a success story of actually using this whole machine learning plus spiking network approach to a real vision problem. Okay, oops. So that's for the kind of pure application point of view. Now there's another aspect to this which is interesting. I told you that I'm interested in how these hardware can learn online in real time. Well, it turns out that these three terms of this update, which may seem cryptic to you, actually can be translated into something that is related to error or downstream error. Something that is like a postsynaptic term. You can see that this one only depends on the membrane potentials of the postsynaptic neuron. And this is something that if you compute it, you'll see it's just like a presynaptic trace. So it actually defines you a synaptic plasticity rule that is, and it tells you what the synaptic plasticity rules term should be in order to implement gradient descent on a particular loss. What this means is I can go to a hardware engineer and say, okay, this is the learning rule that I need in order to implement my loss function or a class of loss functions. But I have a mathematical handle on what these terms should be. I'll tell you a little bit more details on this. You probably know this story pretty well, but it's just to make the connection to the neuroscience more evident. So we have here two neurons, so red one, black one. This is the work of Mark Rum several years ago. And each of these dots represent some connections. And what they do is that they elicit some spiking on one of the neurons, and they look at the elicited EPSP, so postsynaptic potentials on the target neurons. And what they see is that after a while, basically the weight increases. So this is a classical Hebbian effect, and it happens more if the events are occurring. So if the postsynaptic neuron fired when the input arrived. So something that's related to the spike timing. So this led also to these local spike timing dependent plasticity rules, which actually can be explained in a really simple way. So we have two neurons here, so orange one and the green one. When the orange one spikes, so you get this bar here, it creates this trace. How that's implemented is not of interest to us in this mathematical framework, but you can imagine some calcium concentration that decays over time, okay? Until now, nothing happened to the weight, which is constant. Then the postsynaptic neuron spikes. When that one spikes, it essentially reads the state of the trace on the presynaptic side, and writes so it increases or changes the value of the weight proportional to that. The weight doesn't change until the next spike occurs. So when this spike occurs, then you read the trace of the postsynaptic neuron. In this case, because I've used a classical STDP rule, it decreases the weight by amount proportional to that. So this is a simple way to understand how these spike timing dependent plasticity rules work. And this is an online implementation of it. Okay, now what we're doing is actually not spike timing dependent plasticity, but it's very close to it. If we add to this a higher level modulation that's carried by some neuromodulator, which can represent reward or error, essentially what it does is that it's going to modify how we change these weights. Now, why do we want to do this higher level input anyway? Well, these two neurons, they don't know anything about the inputs or the outputs if they're inside a network. And that has a real problem if you want to learn in a large network. And these are basically the hidden neurons in that network. So this modulation essentially gives some information about the outputs back to those neurons. And by applying this modulation is just basically changing the magnitude of these weight updates. So now you can see our gradient-based rule really corresponds. So this green term is something that is like this postsynaptic term here. This orange term here is the presynaptic trace. It's exactly the presynaptic trace. And this red term here is this kind of magical higher level input. So this is how you can understand how gradient-based learning, as people are doing in machine learning every day, is related to models of learning in neuroscience. This was coined as a 3-factor rule because as opposed to having 2 factors as an STDP or Hebbian learning, 2 factors being post and pre, you have a 3rd factor. In fact, you can have more than 3 factors, so it's more like 3 and more factors. Okay, now, there's a problem with this, and the problem really happens on this term here, or this higher level term here. How do we actually compute this? How do we know how a neuron should change its weights, a neuron that's deep inside a network, so there's several steps upwards, several steps downwards. How do we change its weights, right? Even if we know the error, well, it's going to go through several transformations before affecting the rest of the network. So that's called the spatial credit assignment problem. It's a problem that backpropagation solves surprisingly well. But we have a problem that backpropagation is not compatible with local learning. Remember, I mentioned that what we're in some ways trying to do is to build learning rules or dynamics that use only local information. Well, it turns out that backpropagation has some issues with locality. So we need to find other alternatives to solving this spatial credit assignment problem. Whatever I'm saying here is also very relevant from a neuroscience point of view, all right? Because those neurons also need to know what the eligibility or the modulation should be. So in backpropagation, what you do is you propagate activities forward, then you have the error, and you propagate them backwards through the same network, but through basically the gradient of the network. The fact that you have these 2 arrows here that point in 2 directions, it actually reflects the fact that you need to have symmetric connections. Just that alone already makes it incompatible with neuroscience because we can't have 2 neurons that have exactly the same weights in both directions. But there's other problems to this. Backpropagation really works in 2 phases. So you go forward and then you get the activities. In the meantime, you have to save all the activities in your network, and then you have to backpropagate. And so we have this 2-phase learning, which also doesn't work really well. There's some suggestions to solve this. One, which is that, well, it turns out you don't need to have exactly the symmetric transpose in the backward phase. You can have something that's random, that you don't change, but you still propagate the errors backward. It works surprisingly well, but not as well as backpropagation. This still requires you to go through every layer. But there's another rule where you basically just broadcast the error or the reward to the rest of the network randomly. And that works just as well as feedback alignment. So that's a really compelling story for like neuromodulation and dopamine and so on. Another, and I think the most interesting one, is the use of so-called local errors. Now, this is an architectural change. It's a little bit of a kind of a dark area because we don't know what mathematically is happening. But instead of having one global loss function that says, okay, here's what we want to do, and we just try to optimize for that loss function, we add a bunch of smaller loss functions to the network. By smaller, I mean they're local to a given layer or a population of neurons. And then we do just backpropagation here, but we don't backpropagate further. You see there's no blue arrow here indicating that the weight updates here do not depend on what happens here, or not directly. So in practice, I'll already tell you, this is what works best. Among all these 3 alternatives, this is the one that works best, and it's complete. It can be completely local, but it begs the question: what should those local loss functions be? Right. So how can what loss function should we attach to a population and give it reward for solving a problem? Given that it doesn't actually go, you don't read the output of the network, but only the local states. And this also relates to the question of, let me just quickly check time. It also relates to the question of what are the loss functions in the brain, right? If we do believe in the story of gradient descent, or at least to some extent, well, what would these kind of local loss functions or local reward functions be? It's not just the reward of your task, but it would be some intermediate reward that's to define. I'm not going to answer that question. I don't know that, but from the neuroscience community, there's a lot of interest in that point. In practice, you can do something really simple. You can say, I'm just going to build little classifiers here. I just want this layer to do well at classification and this layer to do well at classification. If you have labels, you can do this, and this tends to work best. It does require you to have labeled data sets, which is not really nice, right? We don't have labels to everything that we do. There are some other interesting work in this direction, which I'm going to present briefly. One is predictive coding. It's the fact that you try to reduce predictions between every layer, and that can be a local learning rule. There's the work of self-supervised learning, where if you see a cat now, it's likely that you'll see a cat later. So any transformation in between is something that you would like to use as a learning signal. And there's also some reinforcement learning methods, which I'm not going to talk about. But just in this, giving a few examples that do work. So we built a couple of years ago already this network, which we called the Deep Continuous Online Learning. I was really, in this case, trying to solve the problem of local learning with spiking neurons. We use here these local classifiers for every layer of a convolutional network. And this surprisingly gave us very good results, in fact, better than everything people had published at that time. And it was fully online, and it was learning quickly. So I think there's some better results on this now, but the fact that this was learning online actually makes it unique even now to achieve so well at this task. This is a gesture classification task, by the way. So this is one of those labeled learning cases. I don't have examples for unlabeled work that work well, but I'm going to give you a few pointers here. One which is by my student, Nick Alonso, who just had a paper on this at NeurIPS. And he's using an approach called Inference Learning, or what we usually call predictive coding, where the function that you're trying to optimize is some loss. It can be like classification loss of just at the last layer. And these local predictions basically have some targets, intermediate targets at the intermediate hidden layers, and some predictions that the previous layers have generated. And you just optimize this function in a special way. You first optimize the targets, and then when you're done optimizing the targets, you optimize the weights, and you do this back and forth. This actually existed since a while, but what my student has shown here is that this is equivalent to a form of gradient descent, not the usual one that we think of. It's another one called implicit gradient descent, when the batch size is 1. Remember, in machine learning, usually you train in batches. Well, this only works with batch size 1, which is tough luck if you want to make this work on the GPU. It takes forever, but that's what the brain does. So it was very interesting from that point of view. So predictive coding is one way of building these local learning rules with gradients. Another one that I really like, this is by Friedemann Zenke in Basel. They use this, they ride the hype on these self-supervised contrastive learning. Really, as I mentioned earlier, so if you see a cat now, you're going to see a cat then a second later. And just using these kinds of losses of similarity between these two data samples, they can have this layer local learning and really learn. This is the accuracy for the multiple layers, where you're not back propagating between layers at all. You're just learning locally. So this is another success scenario. It has a lot of problems itself. Now this one relies on batches. You cannot do this without batches, which is a real problem from a neuroscience point of view. But it is a very compelling approach in itself. Okay. Now, all this story is great, but did we actually solve the problem of learning online? And this was a little bit the discovery I made when I was working on all these things. The experiment was that we built this cool simulator, and later it was even working on the Intel Loihi chip. And we said, okay, let's try to teach it MNIST digits, and we just basically showed it handwritten digits. And it did learn the digit 1, it learned the digit 2 and the digit 3, and then you go back and test the digit 1. It's like, oh my gosh, completely forgot everything about it. So you have to repeat it again. And then you present digit 4 and you have to repeat it again. And so in the end, this whole system that we built was useless from a practical point of view. It was nice maybe from a theoretical point of view, but we couldn't use it in practice. So there's several reasons why this is happening. One you might already know is the problem of catastrophic forgetting. Conventional neural networks tend to forget what they've learned if you don't repeat the data. And that's just because how the learning formulation is done. In order to learn, you basically need to present the data in an independent and identically distributed fashion. If you don't do this, then you forget. Learning is unstable and you get catastrophic forgetting. It's very data inefficient. We had to really show it these digits a lot of times for it to learn anything. And so really teaching a blank neural network to learn, it takes a lot of time. And it's if you consider that the real world is basically one sample at a time and not batches of data, this makes it an extremely slow and unappealing learning platform. So how can we solve this problem? I think it's pretty clear that coming back to this example of the tufa in the first slide, we don't learn from nothing, right? That tufa actually looks something like a flower. And so you can then relate this to what you've learned as like a flower and look for other flower-like items. So it's clear that we don't build from scratch. Our knowledge from scratch, we build it on what we've already learned. And so that's something that we are moving towards, which is really learning in multiple stages, hence the kind of description of bi-level optimization. So in the first stage, you do the learning offline and off-chip. By offline, I mean it can be in a big computer that may be very expensive to run in terms of power. But it's there, and we can do it. Once we've trained it, we pass those parameters to the online chip. This should be online and on chip. Sorry about that. Where we don't have as many learning capabilities, but we're able to learn where the data is acquired from. So that's the idea, basically going from simulations to emulations of your network. And by doing this, you go from high energy to low energy, and hopefully solve the learning problem in the real world. So one way to solve this problem, there's several ways of solving this bi-level learning problem. One that we liked was called this model agnostic MetaLearning. I won't go through the details here, but what it essentially does is to learn the learning rule, and it does this in a purely gradient-based way. And we can do this even with spiking neurons because we've just shown that it actually is somewhat compatible with the spiking neurons. And what it does is that it finds so in the early stage, so the offline stage, you learn the parameters of the network such that it only needs a few updates on the chip in order to learn quickly. You can even feed some of this data back to the to the offline learning loop. Okay, so that's basically what I was saying. This meta learning stage can be very expensive to run, right? So you're basically calculating the gradients of a learning algorithm, which may lead to second order gradients and so on. So it's expensive. This is something that we need to solve, and my student Jan Finkbeiner has actually been looking into acceleration of the training of these spiking networks. Now, one thing that spiking networks do really well is that they're sparse, right? If not very active, and you have also sparse connectivity, they can be very efficient to train and to run. But we don't really have the computers for doing this. I mean, yes, we have neuromorphic hardware. It turns out neuromorphic hardware is not a good platform for prototyping. We actually need supercomputers for these. So what is in between neuromorphic hardware and a GPU? So one of the candidates here are these computers from a UK-based company, Graphcor, which are really trying to go head-to-head with NVIDIA on building machine learning platforms. We're not so interested in what they can do on a machine learning perspective, but on their particular architecture, which is basically thousands of processors with their local memory. Okay, so that's very much like a neuron. And so Jan has been looking into programming this computer at a very low level and taking advantage of sparsity. And he does find that if you go at sparsity levels of 90, well, any sparsity level here, actually, you are faster by some very good factor compared to the best GPU we had. These are still consumer GPUs, but these are, we've tested also with A100s, A100s, if you're familiar with that. This is actually faster than the A100. And so we have this platform that can do 10 times faster training compared to GPUs. This is all training, by the way. So it's a very appealing approach. It might also be interesting for large-scale simulations of spiking neurons. They're also cheaper than the kind of HPC graph GPUs that you get from NVIDIA. Okay, so that hopefully, or solutions like this, will solve the problem of doing the offline learning, at least make it faster. And going to the learning at the edge, well, we do need some hardware that can do learning at the edge. One of my students, so Kenneth Stewart, worked with the Intel team. Actually, we were involved with Intel when they were developing their Louis chip, so we know pretty well how it worked. We tried this idea of transfer learning. Now, this is not exactly meta-learning. It was before we got into meta-learning, but we were basically teaching this network gestures as we have it from the data set. And then Kenneth was showing the gestures on his own with our sensor, which can be connected directly to this chip. By the way, I should have mentioned this is a digital neuromorphic chip. It's probably the most advanced platform that you can use now in terms of usability, but it's digital. So this approach could basically learn these new gestures very quickly. I do have a short video here if this works. So that's Kenneth who's showing basically new gestures. That's not one that's in the data set. And you can see that every time he's actually doing these gestures, he's also discreetly pushing on a keyboard button because that's how he gives the labels. As he shows some new pattern, he needs to also say that what the label is. This is one of the issues we're trying to solve in order to learn without labels. So now he's still teaching the network one gesture after another. And in this case, he doesn't need to do repetitions. So just in a few seconds, he's going to repeat the first one. This, by the way, the y-axis here shows the firing rates at the last layer. There you go. So now he's repeating. There you go. So that was like a one-shot learning of these gestures, totally online and on chip. And we could, and that's the Italian. Okay. All right. And so we still haven't fully done this on hardware yet, but we're also applying this idea of meta-learning onto these chips. It's a little bit of a complicated figure, but what we're trying to do is to learn how to learn using the particular learning rules that are on this Intel Louis chip. This is working well in software. In fact, we get results that are almost as good, or sometimes even better than the equivalent artificial neural networks. Okay. So this is my summary slide, at least for the meta-learning part, which is that this whole meta-learning actually it has a really appealing aspect to it. Of this learning to learn, which is that the learning rule that I need on my chip or on my model is actually very simple. If you're familiar with machine learning, generally you optimize with some rule like Adam or other fancy rules that actually make copies of the weights and need to keep multiple traces of the weights. There's nothing of that here. The learning rule that you use when you learn to learn or train to learn, as we say, you only use the simplest gradient descent update, which is very easily implementable in hardware, but also something that you can interpret pretty well from a neuroscience point of view. So there's the idea of simplicity. You can train to learn in a simple fashion. It's very memory efficient. This is especially interesting from a hardware point of view, but also from neuroscience. You don't need a lot of bits of to store weights. You know, if synapses are in the 5 bits range, well, that's not good enough for doing learning and machine learning in most cases. Well, it turns out you don't need that, because if you're learning quickly, you need to make big updates anyway, and big updates means that you change the weights a lot, relatively speaking. Endurance, this is a problem for hardware. It's a single weight update, so you're not going to have problems of the device wearing down. Quantization is, we can also train to learn with quantized weights. So if you say that I know my weights are 5 bits, I can train to learn with 5 bits. So further simplifying the learning rule. And flexibility, as I mentioned, so as in the same way as we can learn to learn with simple learning rules, we can actually recruit any dynamics in the network for learning. There was some really cool work by DeepMind that was showing meta reinforcement learning, how they're doing reinforcement learning with prefrontal cortex activities rather than prefrontal cortex weights. And so you can imagine that you can also learn with just working memory. And robustness, which is that you can, even if your plasticity rule is not exactly what you need with respect to the algorithms, you can actually mitigate this by learning and trying to learn parameters that would basically fix to some extent the non-idealities of your rule. So there's a lot of interesting points here from an engineering point of view, but also from a neuroscience point of view. If you think of, so how much plasticity does the brain actually need in order to learn a task, given that I've started with some prior knowledge? And this gives you some framework to actually answer that question. Okay, so that's the end of my talk. I'd like to just thank the people who have worked with me on this. So that's Kenneth here. This is actually my institute plus another institute, but we're working very closely together. So we're about 20 or so people. Friedemann Zenke at Basel was one of my collaborators, also some folks at Intel who also helped us with the Intel Low-Heat chip. Okay, and just a plug here, we're still hiring at all levels. So if any of this is interesting to you, just come and talk to me.